Hello, welcome back to another video. So what we're working on now is still 1D examples, but we're actually going to do vertical examples. And what I mean by that is the previous examples we have done has been along the x-axis. But what happens if we just tilt this up? And this becomes one-dimensional as well, and we can call this plus y. We can also invert this, right, where we start at the top and then call down positive as well. When we do this though, because we're moving up and down, right, we will have an acceleration of gravity. Either it'll be minus 9.8 meters per second squared, or it will be positive 9.8 meters per second squared. We won't have anything but this, okay? Unless it's specifically told that an object is accelerating, okay? So let's, with that, but yeah, we can pretty much use the exact same type of kinematics that we've been using, okay? So let's go ahead and start with example 1. Just a typical, the easiest type of example. Okay, suppose a ball is dropped from a tower. How far will it have fallen after time 1, 2, 3 seconds? And then now suppose the ball is thrown down at a certain velocity, 3 meters per second. How far will it have fallen after time 1, 2, 3 seconds? So I'm going to start like I always start. I'm going to go ahead, oops, it's too exaggerated. I'm going to go ahead and I'm going to make a tower. Okay, we got several windows. There's a dude working. This guy is, how about a guy in a bed is just chilling, he's sleeping. Z's. Hard to do more detail, it kind of looks like a blob now. I don't know. There's like a lamp. Anyway, so we've got a tower. And what I'm going to do for this example is, because we want to know how far will it have fallen. In this example, if I were to make up positive, all our positions would be 0 or negative. And so I'm actually going to make down positive. I'm going to call it positive y. So we're switching from x to y because we're doing vertical now, just straight up and down. And I'm going to call this, whoops, plus y. I'm going to call our y initial 0, okay? And at the beginning, how far will it have fallen after time 1, 2, and 3 seconds? So in this instance, we won't know y final. And in the first case, dropped from a tower. Drop implies 0 meters per second dropped. Okay? And this is for parts A, B, and C. Where part D, it actually says V naught equals 3 meters per second. Okay? The other thing we glean from this is because it's a vertical example, we now have our acceleration, and it will be positive 9.8 meters per second squared. It's positive because we said down was positive. Okay. And this value of 9.8 meters per second squared will be what we use for gravity always. Okay, so if you see the term G, G represents 9.8 meters per second squared. Okay. Some books will just round it to 10. I typically always use just 9.8. All right, so now we can go ahead and solve it, or do knowns and unknowns, sorry. And this is, again, parts A, B, C. We'll have to do a separate list for part D. So our initial position, we start off, I'm defining this as 0. Okay, I'm saying where we're starting is 0. Now the y final, 1 second, or the y final at 1 second we don't know, y final at 2 seconds we don't know, and y final at 3 seconds we don't know. This is what we're trying to solve for. That's our positions. Our velocity is 0 for initial because it's being dropped. Okay. We don't know our v final at 1 second, 2 seconds, or 3 seconds. So this won't be able to help us out. Our acceleration, we know. So we've done position, velocity, now acceleration, is plus g is plus 9.8 meters per second squared. I'm writing plus here just to be super explicit so that we know down is positive. Our time, we know it. It's 1, 2, or 3 seconds corresponding to these 3 positions. Okay, so whatever the position we're solving for, so we're solving for y final for after 1 second, we'll plug in 1. Okay, so now the next step is picking, so choose an equation. Okay, so if you remember our previous equations, x final equals x initial plus v naught t, right? These are our equations. V final squared equals v initial squared plus 2ax, right? What we're going to do is we're going to convert all of these. This is x. We're going to convert them into y. So they're basically the exact same formulas. Okay. You may see a g here instead of an a, since we always use 9.8 now to represent our acceleration. But yeah, our equations are virtually the same equation. You just swap x for y so that you know you are working in the y coordinate axis now. But same equations. For this one, I think I want to use this guy because it has time and it has acceleration. The ones with v final, we don't know. Oh, one quick thing I should actually mention. This guy, we won't use unless a equals 0. So this is a special case. You really only have 3. And same with, you really only have 3 just because, again, unless you have to have a special case where they explicitly say you're not accelerating at gravity for some particular reason. So you'll really only have 3 equations to choose from, okay, when you're working in the y coordinate axis. So this is the guy we're using. I prefer, even though you'll see it written as G in a lot of textbooks, I prefer to keep it as A. That way you plug in A equals either positive G or negative G, right? This is more generic. So I keep it this way until I apply it. Because if we wrote plus 1/2 G here, and then we plug in, you know, say we have a negative G, but we'll think it's a positive G, right? So you can see how it can mess up your signs. Anyway, so I'd say keep it like this and then plug in G, either positive 9.8 or negative 9.8, as you see fit. So our initial here is 0, right? We're starting at 0. It's being dropped, so that guy's 0. So y final equals 1/2 at squared, where our time will be 1, 2, and 3 seconds. So y final at 1 second will be 1/2 9.8 positive, okay, times 1 second squared. So y final at 1 second, half of 9.8 will be 4.9, times 1 squared, which is just 1. So we'll have second squared times second squared cancels. We'll be left with 4.9 meters. Okay. The next one is 2 seconds. So that's answer number 1. We just do the same thing now. We plug in time is 2 seconds here. Square it. So we'll have 4.9 times 4. This actually equals 19.6 meters. And then y final 3 seconds. So now we're going to get 9 over here. We'll multiply that out. We get 44.1 meters. Okay. One thing I want to point out is y motion is parabolic, meaning if you look at this equation, and then these guys were 0, right? So we could just get rid of those. But even if they weren't, it would just introduce a constant, and you'll see that in the next part. But y final equals, a parabola is y equals x squared, right? Or y equals a x squared, where this is just a constant. And this will adjust the shape of the parabola, how wide it is, right? This is if a changes. And of course, we have the dotted line over here. But this guy serves as our constant, okay? So we have 9.8 t squared, right, where this is just our a, and then this serves as our x. And so you'll notice it's just a parabola, okay? And so our position per time, right, after 1 second, 2 seconds, 3 seconds, 1 second, increases faster and faster, each position change, because we are accelerating at g. So 4.9 meters, 19.6 meters, 44.1 meters. So your position is changing faster and faster and faster. So your velocity is actually increasing as it drops, right? Now, it won't increase forever, right? It's not like it will just keep accelerating until it hits the speed of light. If you had a tall enough tower, you'd hit terminal velocity at some point, which is where it would stop accelerating. And the reason for that is air resistance is a force. So if you have something falling, okay, you have the force of gravity pulling down, and you'll see this is known as we'll talk about forces and what I'm doing here in a second, but you can imagine gravity points down. You have another force that points up, and that's air resistance. And air resistance actually increases, so it grows over time as your velocity increases. And you get it to the point eventually where it perfectly counteracts gravity, and so you stop accelerating after a certain amount. Just to explain that, why you don't increase forever. But yeah, that's how you do this particular problem. Let's do the second part, so part D. We now have a V0 of 3 meters per second under knowns. Okay, the other stuff is the same. So we're still going to use this guy. And we want to know what our positions look like now. So y final 1 second equals y initial plus v0 t. And so now we can't get rid of this because this guy is now 3 and not 0, but we can still get rid of the y initial. So equals our v0, 3 meters per second, times 1 second, plus, so this is just a new number that we have. So 1/2, 9.8 times 1. Okay, that's a meters per second squared. So this will be our typical 4.9 plus 3. So this will be 7.9 meters. Okay, and then the next one times 2 seconds. Okay, 6 plus our original 19.6, so this is 25.6. And then we have our last one. Okay, so this is 9 plus our 44.1 meters, which totals 53.1 meters. And so all this additional velocity does is it starts your, instead of starting at the origin, it just basically does this, moves it up a little bit, and then kickstarts your parabola. So it would look something like this for 1 second, or for the first one, for the second one, for the third one, okay? Where it's going longer and longer. But it just increases a constant amount. And it increases it constantly because your time here isn't squared like it is over here. Okay. But yeah, when you're solving vertical problems like this, you do the same steps, you still draw it, you do knowns and unknowns, and then you plug in. Or you pick the equation, then you plug in. And here, you even have less equations to pick from. So if you're doing for the most part, unless you're told it's not gravity for acceleration, like you're told there's no acceleration. But you pick your equation, then you solve, right? So in some respects, it's easier than horizontal kinematic examples or kinematic problems. So keep that in mind. Okay, so let's do example 2. And this is the final example. I know that's crazy after we did, the last one, there were 5 or 6 examples, and most of those were long. This example kind of covers a lot of problems because it really goes into a lot, right? It's a very in-depth example. So a person throws, so here's the example. A person throws a ball upward into the air with an initial velocity of 15 meters per second. And we want to calculate how high it goes, calculate the time it goes for the ball to reach the peak of the motion, which we're calling y max, and then calculate the time it takes for the ball to come back to the hand, and then calculate the total time the ball is in the air. So there's actually a lot for this particular problem, okay? So let's look at this. Real quick, we're going to draw it, okay? So we're starting at y initial. We throw the ball up, and then it comes back down, right? So it goes up and back down. So what I'm going to do, we're just throwing it up and down. What I'm going to do is I'm going to draw this like this. Now keep in mind there is no x distance here. It's not actually traveling left and right. I'm just drawing it this way for illustration. Okay, so no x distance. Drawing is so you can see up, down motion. So you can see the up and down motion clearly. Okay. Our y final is technically when it comes back to the hand. So we're examining the motion when you throw it up into the air and then come back down. But up here they tell us is y max. Okay, we don't know what that is. Peak of the motion, y max, but we don't know what that is. We have an initial velocity, it tells us. Is 15 meters per second. And we don't know our final velocity. Coming back to the hand. One thing I will make note of, just in case you're wondering, your final velocity isn't when you're holding the ball. It's the instant before your hand. So instant. Because the reason for that is if you were looking at it from hand to hand, it would be like you didn't throw the ball up, so there's no initial velocity. And after you catch it, it would be 0. So it would look as if the ball has just been in your hand the whole time. So we usually examine the instant right after you throw it and the instant right before. Okay, that will be true as we carry into 2D kinematics as well. You always look at just the instant in time right before. That way you can examine the motion you care about. We don't know times. So it wants the time it takes for the ball to reach the peak. So I will call that time 1. So this half of the motion. And then there's time 2. And then there's t total, which is t1 plus t2. We don't know any of the times. So that's a lot of information. Let's go ahead and do knowns and unknowns and try to see what we can do. Keep in mind, the only thing they actually told us here was the initial velocity and that we're throwing the ball. All this other stuff that we're getting comes from us examining the problem. So our initial position, y initial, is 0. We're in the hand, we know it. Our y final is technically when we just get back to the hand. Okay, so these guys aren't that useful. Our v initial, however, is pretty useful. And we don't know our v final. There is one more position that I forgot to neglect. So we don't have just initial and final. We have max. So our y max is another number or another value now. So we actually have 3 positions. We have our initial, final, and max. And our max is the peak motion. Okay. So now we can do this 15. Yeah. Final, we don't know. And our v max, so the velocity at the max, we didn't write this down, but let's talk, well, I'm going to write this as an unknown for now, and then when we examine it, we'll talk about this, okay? We know it, but it's not told to us, okay? I'll show you what we know about this. So now we've done position, velocity, next one's acceleration. A equals, now, we haven't really defined a coordinate system. I'm going to just say up is positive, and I'm doing that because it's going up and coming back down, so we'll have negative motion no matter how we do this. We might as well just make up positive, okay? So that means that this will be minus 9.8. So up, positive. Now we need our times, right? We don't know time 1, which is the time to the max. We don't know time 2, which is the time to back to the hand from max. So this is to max. This is max to hand. And then we, of course, don't know total time either. But we do know that it's T1 plus T2. Okay, so there is a lot of information we don't know. And we really only know a couple things. We know these guys are 0, these guys are, minus 9.8 and 15. So let's see what we can do. Let's list some equations out and see what can help us. Okay, so here's what we got. Let's look at this. We don't know time, nor do we know position. So this would be, we want to get y max or y final, okay? That's one of the things we need to know. That's literally calculate how high it goes. And I don't think this can help us because we don't know this and we don't know time. So we can't use this guy. So we're forced to use these. So let's look at this. We don't know time. This guy we can't use either. V final squared and V initial. So V initial squared, we know it. We know this. We don't know V final, which would be V max, right? This is technically V max. But we know our position. So if we can figure out V max, we can go ahead and figure out our position. So if you think about this, when you throw a ball into the air, you throw it up, and it reaches the peak of motion, what happens in a very brief instant of time? It stops moving. So stops moving briefly. If it's not moving, its position isn't changing. If position isn't changing, that means V, which is change in position, over time would be 0, right? Which means our V final or V max at the peak is 0, okay? And so this is true. When you throw something up in the air, your V max is 0. What people typically confuse this as is that, so V here is 0. V initial we have, V final we have, but our V is 0. What people typically think is that our acceleration is 0 at the peak. But that's not the case, because you're still on Earth, you still have the force of gravity on you, so you still have an acceleration of 0. So A is not 0. A still equals 9.8 no matter where you're at, okay? It doesn't matter. The ball right here has an acceleration of A, has an acceleration back in your hand, has an acceleration right here. From gravity, I should say. Your net acceleration changes when it's back in your hand, obviously, because you're holding it. But you still have the acceleration from gravity. I have the acceleration of gravity right now sitting on this chair. The reason people think this is because you don't see it moving. If it's not moving, how can it be accelerating, right? And so acceleration, this is one of the problems that people have with physics in general, is if you can't see it, it's hard to relate to. But if you think about it, acceleration is one step removed from being able to be seen. You can see position changes. And because you can see position changes, you can see velocity. And so you can see velocity and position. You can't see acceleration as easily. And so people tend to confuse that. But make no mistake, your acceleration is 0 here. Okay? Or your acceleration is, sorry, 9.8 here. Your velocity is 0. Okay? Try to keep that in mind. Okay, you still have that force acting on you. So, knowing that, we can solve for this. Okay, so now solve for y max using v max equals 0. So, v max, I'm going to rewrite the equation instead of v final, I'm plugging in max. Okay. This guy is 0. And we are solving for y final. So v squared max. Oh, this guy was 0 too. So we have 0. And this is a technique we'll also use during two-dimensional motion. So we're going to subtract this over. And remember, from the previous example, you want to keep the negative on the outside. To A, sorry. And this is going to be 15 squared over 2 times minus 9.8, which is great that both are negative because we're going to get a positive answer. And so what we tend to get from that is 11.5. So y max, sorry, that should have been max the whole time, is 11.5 meters. Okay. So that means we're throwing the ball up, back down at the peak. This is 11.5 meters. Okay. All right. So now we know the peak of the motion. Now we just need times, I believe. So we go back. A lot of these problems are long, so you lose what you're trying to solve for. Yeah, we just need times. My advice, split it up. Solve for T1, then T2. And then T total, you just add the two. So T1 is this part of the motion. This is T1 right here. It goes from y equals 0 to y final is 11.5 meters. We have our initial velocity here, and we have our v final is 0 up here. Okay? So if we use the formula that we didn't use before, the one with time, which we couldn't use before because we didn't know, well, we hadn't reasoned yet that v final was 0. We can now use this. So we plug in, so we say this guy's 0, so we say 0 equals v initial plus at, subtract over, and this is going to be T1. And this equals 1.53. You must be wondering, why didn't I use the fact that we've just figured out position? You can. You can use this equation now, the one that you just figured out, because we now know y final. The reason I don't is because we have this squared thing here. This would have been 0, this would have been something. So this is this equation is more complicated. So if I can avoid it, I won't use it. So I'll avoid it if I can. I would stick to the simpler formula. So this is much simpler, right? But if you plug in the values, you'll still get 1.53. It's like I've been saying, you can take different paths to get to that same answer. Okay? So, now that we've solved for T1, let's solve for T2. So, here's our situation. We start here. 11.5 meters is our y initial. Now, we need to completely do a new frame of reference. Our y final is back at 0. For this stage of it, so we're solving for T2, this is the second half of motion. What I would do here is I would just go ahead and say down is positive for this. And I would, so A, positive 9.8. We know our V initial up here is going to be 0. We don't actually know what our V final yet is. So because of that, like right before it hits the hand, right? So we were using this equation before to figure out time, but we can't because we don't know what this is. It's a big mystery. So now we're actually forced. Well, maybe we no. Yeah, this is the only formula we can use without knowing v final. So we're going to use this guy. This guy's 0, or sorry, this guy is 0. This guy's 11.5. This is our 0. And these are our values. So we have 0 equals 11.5 meters plus 1/2, 9.8. Remember, it's positive because we decided down was positive. T squared, we're solving for time. Multiply this over. This is going to be 22, 23. Divide. Meters cancel. And we're left with oh, sorry. When I did this, when I say 11.5 to 0, I inherently do imply this positive. Apologies on that. That up is positive in this instance. If I had said y initial is 0, y final is 11.5, then it would have been down as positive. I know that's confusing. Sorry about that. I realized that when I wasn't getting two negatives here. As I said, it's extremely important to be careful. Okay, so these guys cancel. So we're left with 23 over 9.8 seconds squared. Okay, and guess what you get out of this? 1.53 seconds. Now, this means, this is for T2, so T2 equals 1.53 seconds. This means that T1 equals T2. Now, this actually isn't a surprising fact, for me at least, but it is maybe for you. This is known as symmetric, I guess, motion, okay? And the reason this is the case is you start off with v initial equals 15 meters per second. You go up, you hit 0, and then you come back down. And this takes the same amount of time as this, meaning our v final that we quote-unquote didn't know before is also 15 meters per second. And so if we had just done that and plugged that in, we would have got 1.53 if we had insisted. But we did not because, you know, I told you we didn't, right? So if we were to come up with like another velocity here on the way back down, right, this one would be also v1. And so our velocities going up will be the same magnitude as the velocities going back down. Okay, I hope that's extremely clear. I know this problem is sort of long and involved, but I hope you understand that. And of course, our acceleration the whole time will always be g, g, g. Okay, they'll always be the same acceleration back down. So anyway, do use this fact in the future that our velocities are going to be the same up and down magnitude. Should you see another problem like this, it may be not obvious in initially. That's why I didn't just say, well, we know it, right? I pretended we didn't know it. But do use this fact in the future. This is a very helpful thing. Okay, so we just need total time, which is 1.53 seconds plus 1.53 seconds. This is 3.06, I think. Oh, 1.5. Oh wait, no, it's 3.06. I can't. On my notes, I got it wrong. So, just FYI, my notes are wrong there. Sorry about that. If you're looking at the PDF. So, do, you know, keep this in mind in particular. So, real quick, I know that was a lot to stomach because this is a long and involved problem, but let's just real quick just do an overview again. So, I throw the ball up, it goes up to the peak, then it comes back down. And it does so symmetrically. On the way up, its velocity up will be the exact same as it reaches peak, and then it comes back down. As far as and acceleration is the same the entire time on the ball. Okay, the acceleration always points down, always points 9.8, constantly, because it's still on Earth, right? Just because the ball stops moving doesn't mean it doesn't have that acceleration of gravity affecting it. Now, for problem-solving techniques, the best way to handle a problem like this is to treat it as two separate motions, okay? And you will do that with several types of problems. Anywhere that you can maybe divide it in two to try to get a handle on it works. And we need to do that because we didn't know that v final was what it was, okay? So I hope this helps on vertical problems. They kind of all work the same. Again, they're using just the same thing as horizontal equations. You just change x to y, and you use g as your acceleration unless it explicitly tells you not to. So I hope it was helpful, and I'll see you in the next one.